will try to do a bit of pictures, I mean at least some extract about the visual we did in the piece and the choice of them and a bit their relation. So the piece starts with a pyramid. So actually the projector is placed in top, so we see the projection of a pyramid, which is just then the basis, is just a square. The pyramid has been constructed with the golden ratio, so the height of the pyramid h and the length of the pyramid l. So we have L equal phi times L. For the basis of the pyramid, so there would be the triangle, which is already one face of the pyramid. There would be the square. There would be, later, we will see the hexagon, which has 6 sides. There would be also, I mean, the pentagon doesn't appear, but actually it appears because, so the pentagon is like this shape. And if we take a pentagon of side 1 here, then this diagonal is like phi, the golden ratio. So, and so we have the square, and from then to pass to the next shape, so the next shape would be a sphere, and so in a plane, if we cut in the middle, it will be a circle, and to relate them both, so this is L of Earth and Moon. So if you imagine that there is the Earth inside, so there, so this is, it means that this is the radius of the Earth, and then you draw the Moon above, and you have actually Moon divided by Earth. So when I say divided, I mean the radius is like 27.3%, so divided by 100 if you prefer. So actually calling this alpha, then for the next circle, so the next circle would be this one. And the radius of the next circle, so if we take this r, little r, then we are r equal 1 plus alpha times L. So not exactly the L, but this r that we have the radius that we add like here. So this, like we called little a, for instance, a, and then we have times a. So that's very important in the whole piece to like really choose, when we pass from one shape to the other, to really choose the ratio according to some properties and particular numbers, like and related to other ratio appearing in nature. At this moment we have a circle, and then we make appear other circle from this circle, so there is a center. It's like called the seed of life, so they would be actually like this circle, and then there would be this circle, and then so there is 6 circles more the one in the middle. All the following shapes are really built from these shapes, and afterward there would be so this is the seed of life, there would be the fruit of life. And another interesting point is that when I talk about polygons before, and like with the square, triangle, hexagon, and all those polygons, you can all put them in a circle. And if you go on like this, in the same circle, and add a lot of vertices and make a regular polygon, so all the sides have the same length, and if you go on adding more and more vertices, at the end the limit is a circle itself. And that also justifies the passage from the square to the circle by taking this limit. So then, from the seed of life, actually you can go on this intricate patterns of circle. It's related to, in mathematics, a tessellation of plane and actually a triangular grid that you can put. So the tessellation is just a word to say like the patterns you got when you have tiling in the floor sometimes. So, and you can afterwards cover the whole plane like this, so the whole surface. So afterwards, from this pattern emerge, and from the flower of life, which is built, emerge, so the fruit of life. So the fruit of life, it's really based, like this one, the both are really based on the hexagon and on this 6 symmetry. So there is like 6 circles around, and you will see also here, there is the same 6-fold symmetry. So you have one center, it's all circles of the same size, and they're like drawn on 3 lines there. And so this is the fruit, and actually from this piece, you see if I like draw the center of the different circles, then I will get here an hexagon. And actually I could draw also the bigger hexagon. But this, what is interesting afterwards and what leads to the next figure, is that from this can emerge a cube. So this is a 2-dimensional drawing, but if you see it as a projection of a 3-dimensional volume, if I draw like at this line, you will see like this looks like a cube, like a 3-dimensional cube. So imagine also there is the lines behind, and it's a projection of a cube. And the same for the big one. The big one, you can see it as a cube here, and so there is the lines behind. So cube projected like this. So actually, from this naturally then emerge what is called the Metatron Cube. It's basically one smaller cube inside a bigger cube in 3 dimensions with all the line connecting. So I could take a third color with all the line connecting the different also the 2 cubes together. So there is also the line in between, like there in the Metatron that appear here, here, here. And there is also the diagonal. So you have the diagonal between the face of the cube that appear. And what is interesting about the Metatron Cube and what also it appears a lot in the sacred geometry is because you can see in the projection of this Metatron Cube, which is which appear there in the piece, you see the projection of 4 of the 5 platonic solids. And you can see the 5th one if you distort it a bit, but at least you see a 4th of the platonic solid. So I can write Metatron Cube. And so afterwards, so from this emerge a cube. So what in the show, the lights are projected always in a surface, so even in different surface, but still in 2-dimensional projection. So the space and the beam of the light create the 3rd dimension for the visual. But for the sound, we really computed the different the shape in 3 dimensions and the different points that you have here. So imagine here above you have a cube and another one inside, and the sound is really moving there, and the delay is really happening inside the cube. So the next step would be from these pictures emerge a Merkaba. So a Merkaba is also naturally emerged from this pattern because also always on this 6 symmetry. A Merkaba actually is equal to 2 what is equal, but to 2 tetrahedrons. How do you shape a Merkaba? Is with 2 tetrahedrons. What is a tetrahedron? So it looks like a pyramid, but the only difference is that it has a triangular basis. So instead of before that the pyramid has a square as a basis, here the basis is like a triangle also. So it's all also the triangles are all the same size. And for the Merkaba, you take so one tetrahedron like this, and you could take another one which is reverted. So actually, the other one would look like, so they are intricated one into the other. So you imagine you revert the tetrahedron. So it looks like a star, actually, a bit. And so this is the Merkaba, and then, the final shape of the piece is a torus. So a torus is usually like this. So you have like a donut in the food industry. So very popular, actually. So you often see it like with those two, in mathematics, with those two paths on it, two curves, because you see it's loved, let's say art, by topologists. It's a toy example, which for those guys, they looked actually at volume up to continuous deformation. So for them, they would say that when you have a sphere, for them it's the same, so equivalent, almost the same, than having a point. So this is a ball is the same than a point, and it's the same if you want also than a glass, for instance. Because you can still press, imagine if it were Play-Doh, you can still press the space and contract them to a point without tearing the thing or without gluing neither. So up to a homeomorphism, you can pass from one to the other. So this is too simple, it's trivial. So it's the point is triviality in mathematics. But then the torus gets interesting because actually the torus because of this hole that you cannot compress, actually the torus is like a torus, but it's also like a cup of coffee, which is a famous joke among the topologists that the topologist cannot recognize between a donut and his coffee, the difference, because for him it's the same. As a three-dimensional volume, actually there is an equation. So the equation in three-dimensional coordinates, so imagine you get the z-axis. So imagine your donut is on the ground, you get this z-axis over the sky, you add x-axis, and then you add a y-axis. Then the equation is you have a big radius, which is from the center to the middle here. So this is actually, I could draw this line there. This is actually r. And then you get this small radius, which is here. This is little r, let's say. So this is big, capital R, and little r. And then with this notation, because you need to have precise this, the equation is you have r minus square root of x squared plus y squared plus z squared equal r squared. And this is the equation of the torus in 3 dimensions. So with this equation, if you want if you have a software and you want to calculate the coordinate of the point, you need what is called a parametrization. So actually you need to say, to have some parametrization in function of another parameters of x, y, and z to have this. But this equation summarizes the torus. And what we did in the piece about the torus is that so first, the piece in the torus, for us, we take the big one is equal to the small one. It means it's like an apple. So it means that the center is like a point. So it's the same radius. So actually, it looks more like this. This is from above, imagine, it's hard to draw, but like an apple. And we actually did some curves on the torus. So we did 2 curves. And this is also, it's important because it's the final moment. So actually there is curves which are one-dimensional on the surface of a torus, which is two-dimensional, and happening in a space which is three-dimensional. So we did at this moment like 3 different movements on the torus. So the first movement is like some points that are doing these circles, gamma 2, which is a path on the surface of the torus. So this is the first movement. The second movement, and it's all movement that we map to the sound. The second movement is a spiral. Actually, originally, so the spiral is like something like this, and this goes again. And the equation of the spiral, so it's a logarithmic spiral. So the equation in polar coordinates. So polar coordinates mean that when you have your plan. So this is in a plane for now. You have x and y. So this is the usual Cartesian coordinate, but when you are a point, you can also choose to express in function of theta, the angle, and little r, the length between the point and the origin of the. So in this setup, then this is simply r exponential of b theta, and actually r and b are just constant, so you can choose them any, and if you change, it will change a little bit the shape of the spiral, but fundamentally it will be the same mathematical curve. But of course, it changes then the value a bit, and it will change a bit the how fast it goes, like the curvature here a bit. And so this is one first thing we just we put afterwards on the surface on the torus. The other is like, which is called the rose curve, and which are, as an equation this time, r equal cosine, so cosinus of k theta in the same polar coordinate. So actually, it's really depending on the value for this one of k that you take. So if you take when I say n divided by this, because it's an integer divided by an integer, you can have very different shapes. And what is also interesting is that this k is not rational, so it's not in this form of integer divided by an integer. You get also a curve that will not be closed and could be dense in the plane. So yeah, this is the third curve that we mapped to on the surface on the torus. And yeah, afterward there is also, a lot of interesting things to say about the torus. Like in topology, for instance, they count the number of all, and it's called the genius. So it's called genius 1. And this is genius 0. The torus appear also in a lot of different places. And about the polygon, so those are the polygon, and then you can, so these are on 2 dimensions. In 3 dimensions, you can, as we talk about it, to make a bit the link between things, we talk about so here the Metatron, but in which we see the projection of the platonic solid, and the platonic solid as the polyhedron, convex polyhedron, whose shapes, whose faces are regular polygons like this. And so there are 5 platonic solids, but you could also try wonder in higher dimension, and in higher dimension, in 4 dimension, actually there are 6 shapes that you can build like this. So those faces are regular polyhedron, and then in higher dimension you have 3, and then you can also check that in higher dimension you have also 3 each time. But yeah, this is already a first quick presentation. Okay, so this is all the things that we use in the piece, and so some projection on 2 dimensions, but remember that for the sound we always use like the 3-dimensional shapes, and so those are just projections that what we use for the sound. And yeah, the 2 tetrahedron and the torus at the end, and the surface. And this interplay between dimension. Yeah, so this is it.